All right, guys, moving right along to our next lecture video today. I'm going to kind of start to bring in some of the ins and outs of matter. Right, we spent some time talking about matter as a whole, and then breaking matter down a little bit, just a little bit, and then also mentioned and talked about physical versus chemical properties, and then physical versus chemical change. Now, we're going to take some of the ideas of what matter is and start to truly break matter down into its actual components, starting with elements and compounds here. So an element, first and foremost, is a pure substance that cannot be broken down by chemical means. Cannot be broken down by chemical means at all. So there's nothing you can chemically do to an element to break it down any further than it already is chemically, right? So if we think about what an element is, right, you guys just recently got your brand new periodic table, right? You got your reference table, which means you've got your periodic table right here on the very front. Any of the elements in this periodic table, not a single one of them can be broken down by chemical means. Again, it's just an element. It's not going to change and break down into anything smaller than that, right? An element is the purest substance that can ever be formed. Now, a compound, on the other hand, is a pure substance, but it's composed of two or more different elements combined in a fixed ratio. So when it comes to elements, elements are essentially made up of compounds. I said that opposite. Compounds are actually made up of elements. So think of elements being the most pure form of matter possible, whereas the step above that is a compound, which again can be broken down by chemical means into its elements. They have different properties from the other elements that they actually make up of them. So for example, if you've got oxygen, for example, and carbon, two different elements, totally different properties, physical, chemical properties, whatever, right? But as soon as you combine carbon and oxygen together to produce, let's say, CO2 or carbon dioxide, it takes on a whole new form. Whereas carbon is most likely not going to be a solid, oxygen is going to be oxygen is of course going to be a gas that we can breathe and whatnot. Whereas carbon dioxide itself is a gas that we definitely don't want to be breathing in, right? So it's a completely different property that consists of the elements themselves. Now, particle diagrams are going to be one of the next things we get into here that kind of help, describe the actual molecular structure, molecular look of all these different things. So they're models, right? We've talked about models since the very beginning of this class, talking about how important models can be, how useful they are, and in terms of how to explain certain things. Right? We use models all the time in our lab environment here, and it's going to be no different in the actual class. So particle diagrams are models used to explain compounds, elements, and mixtures. Now, we're going to literally draw diagrams of these particles. Now, when I say, we're going to be drawing diagrams of elements, compounds, and mixtures, this is what they're going to look like. So, for example, whenever you're looking at an idea of what a particle looks like when it's regarding an element or a compound, these are going to kind of be the examples that we utilize when it comes to what an element should look like in our particle diagrams, right? So, if you're ever tasked with drawing or writing out an element in a particle diagram, these are really the only four different types of elements that we should be drawing in our particle diagrams. You've got one over here, or these two over here, for example, right? These two are going to be ones that really just look like pure elements, nothing crazy here. Now, on the flip side here, we've got these guys right here. I've got this one right here and this one right here. So these ones are a little bit more difficult to understand why they're particles, and they're what's called our they're what's called more of our diatomic molecules. And so diatomic meaning di, or di meaning two. So it's two atom molecules. They are elements, and we'll talk more about that later on. But yes, these four examples are great examples of what an element can be. Whereas these examples here are compounds. Notice the difference, especially the color difference here, right? Whenever we look at our four examples rather of elements here, this is example 1, 2, 3, and 4. And these four examples of our elements here, not a single instance where the colors are changing at all, right? Element number 1 is just black. Element number 2 is just white. 3 is just black. 4 is just white. So the same color consistently throughout for our four elements. Now, when we look at our three compounds, for example, we've got black and white. We've got black and white again in our second compound, and in our third compound we actually have three different colors present here: black, white, and red. So that's a very good indication telling you that you've got two or more different elements in a very, very specific ratio leading to an actual compound. Okay. Now, mixtures, on the other hand, mixtures are a little bit different. They take this idea of our two most pure form of matter, elements and compounds, and combine those two pieces in different various ways. So, plain and simple, a mixture is a combination of two or more pure substances where each substance keeps its individual character or chemical properties. Okay, again, a chemical or combination of two or more pure substances where each substance keeps its individual chemical properties. Now, of course, it's not just something called a mixture. There are, of course, going to be different types of mixtures, and we're going to get into those right now. So, three main ones here. There's going to be mixtures that are element and compound mixtures, so a mixing of elements and compounds. There's going to be mixtures where it's just elements, but the catch here is that it's two different elements. It's not going to be ever a situation where you've got two of the same elements mixed together. That would just be the same element we're dealing with, right? So it has to be making sure that if it is a mixture, it's two or more pure substances that are different from each other. And again, if it's two elements, they've got to be very different elements from each other in order to be a mixture. And last but certainly not least are two or more different compounds here, right? Again, got to be different compounds. It cannot be two of the exact same compound. Otherwise, it's just going to be a pure substance of a compound. It has to be two or more different compounds present in order for it to be a actual mixture itself. Now, how do we go about classifying mixtures? Well, that's a little bit of a different story here. Classifying mixtures is a smidge different than actually the different types of mixtures. These are the different types of mixtures you'll normally see: element, compound, element, and compound. But you can actually classify mixtures and these three types of mixtures even further. And the first one here is what's known as the homogeneous mixture. Okay, homogeneous meaning same. So homogeneous mixtures are composed of two or more substances that are evenly distributed throughout. Evenly distributed. So a couple of different details about homogeneous mixtures. The composition is the same throughout, which is also, like I said, phrased as evenly distributed throughout. They're also called solutions. Now, we're going to spend an entire chapter later on in the school year, around March and April, dedicated to this one single idea known as a solution. So solutions are incredibly important, and again, we spend an entire chapter specifically talking about solutions. So there's a lot to unpack later on in the school year, talking specifically about our homogeneous mixtures or our solutions. So some examples of these homogeneous mixtures are going to be things like Kool-Aid or Lemonade-O. It's good, that's dating me a little bit, but Lemonade-O is basically just like powdered lemonade. You put in a glass of water, you stir it up. Okay, think about if you guys have ever had those Kool-Aid packets or Gatorade packets, right? It's like little crystalline little crystalline powder of Gatorade. You pour it in your water bottle and you shake it up. And now you've got Gatorade, kind of the same thing as Kool-Aid and Lemonade-O. Gas or pulp-free orange juice, right? These are all examples of homogeneous mixtures. They're examples where you can't really see a difference in the actual liquid you're looking at. The other type of mixture here, their classification of a mixture, is what's known as a heterogeneous or different mixture. Heterogeneous meaning different. So we've got these heterogeneous mixtures that are composed of two or more substances, again, but in this case, they're not evenly distributed throughout. Right, so again, looking at the differences between homogeneous and heterogeneous, homogeneous is evenly distributed, whereas heterogeneous is not evenly distributed throughout. So some examples of these situations, and you're probably already, the gears are already turning a little bit about what are some mixtures of two different things that you've seen in the past, are going to be some things that you're probably already used to seeing, right? So oil and water or oil and vinegar, for example, right? Those are two key examples, two really important examples. That you guys have probably seen in the past of two or more different substances mixed together but not evenly distributed. A nice cappuccino, right? If you ever gotten one from Tim Hortons or Starbucks, right? Those are great examples of heterogeneous mixtures. Blood, for example, although you're not really probably seeing blood, hopefully all that often, blood is another example of being a heterogeneous mixture. Pulpy orange juice, right? You can see the difference. If you have a clear glass, for example, you can see the difference between where the orange juice liquid is and where those solid pieces of pulp are, right? So there's a heterogeneous mixture going on there. Sand and water. Sand and water is another great example. If you've ever built a sandcastle at a beach, for example, right? You take a big old bucket of water, and more often than not, in that bucket of water is going to be some sand. No matter how much you shake up that bucket of water, right? That sand is never going to dissolve, right? It's never going to dissolve into the water like your Kool-Aid or like your Gatorade powder is going to in your water, right? So two very different things, sand and water, lead to a heterogeneous mixture. Now, this is a concept map you guys saw recently, more recently in your learning guide that you just did the other day. But this is a great example breakdown of matter, right? Matter can be broken down into two main things: pure substances on the right, which are our elements and compounds, and then mixtures on the left here, which are our heterogeneous and our homogeneous mixtures. And you can see the idea that between pure substances and mixtures, those are where our physical changes occur, right? But when you break it down even further on the pure substance side, elements and compounds, those are where our chemical changes occur, kind of taking a few leaves out of our previous class with chemical and physical changes there. We're going to take a quick break here to talk about techniques to separate mixtures. And this is going to be a nice segue because the next lab we do, lab number 3, is going to be all about separation techniques. And we're going to talk about 4 specific separation techniques here. The first one here is definitely going to be one you guys are going to be doing in lab number 3, which is called filtration. Now, filtration is where you are able to separate substances based on their particle size, making sure that particle sizes that are smaller pass through the filter, and anything that's too large is going to kind of be staying behind inside of that filter. A great example of that is coffee, right? More often than not these days, I know a lot of you guys are probably using Keurigs at home. If you don't have a Keurig, maybe you're still brewing a regular basic pot of coffee. Now, either way, those are both great examples of a filtration technique. If you're brewing a regular pot of coffee, you take your coffee grounds in your coffee filter, you pour the grounds in your filter, and the water goes through the coffee grounds and through the filter. Well, as the water, the hot water, whether it's the K-cup or the coffee filter, goes through that K-cup or goes through that coffee filter, it brings through it, right, the water. The water very clearly goes through the grounds and the coffee filter, but what stays behind is the coffee grounds, right? They stay behind in the coffee filter. They also stay behind in the actual K-cup itself, right? So that's how you brew your cup of coffee without getting any grounds in it, right? So your solid, larger particles stay behind, whereas your filtered liquid or your smaller particles are going to be filtered through no problem. Up next is called distillation. It's boiling, right? So distillation is a very basic separation based on boiling point. So you boil a mixture and it's able to separate their technique or separate their particles based on their different boiling points. So inside of this distilling flask here on the left here, you're going to have several different liquids present in here. Based on their different boiling points, what's going to happen is this liquid is going to start to boil. And if you've got substance A that has a boiling point of 100 degrees Celsius and substance B that has a boiling point of 200 degrees Celsius, you're going to be able to use your thermometer to determine what substance is boiling when. So it's a great way to separate substances, especially liquids that are mixed together here. Up next is crystallization. And it's a separation based on evaporation. So it's when it evaporates part of a mixture away, and whatever is left behind is a mixture of solids and whatever. So if you've ever had rock candy in the past, or you've ever had rock candy recently, rock candy is a great example of crystallization. Especially what happens, or specifically what happens there, is you've got this mixture of water and sugar and maybe some other flavoring and some dye, for example. What happens is the water over time evaporates, and what gets left behind is the actual sugar crystals forming, and that's how you get your rock candy. Last but not least here is chromatography. It's not one we're going to be really referencing too often, but just know that it is a separation based on particle attraction or particle affinity. And more often than not, you're able to use different colored dyes to separate and move up what's known as chromatography paper. But again, we're not going to really spend too much time on chromatography. The other 3 are going to be a bit more relevant to our discussions here. The very last thing I want to talk about in this video is temperature. Now, temperature is the measurement of the average kinetic energy of a substance. Now, all particles in a substance have some amount of kinetic energy or motion. And at absolute zero, for example, it's actually the temperature at which matter ceases to exist, right? So if something is not moving, if matter is not moving, it's not able to exist anymore. And that's exactly what happens at absolute zero. So if temperature is at its lowest point, 0 degrees Kelvin or negative 273.15 degrees Celsius, that is when you are at absolute zero and temperature is at its lowest point possible and matter ceases to exist. Now we've got these two different Temperature scales here, we very briefly talked about Celsius and Kelvin. Again, these are going to be the two different temperature scales we utilize in this class. We are no longer looking at or mentioning anything about Fahrenheit at all. And we're going to talk more about this when I see you guys next, about the difference between Celsius and Kelvin, and get into some examples of how to convert very easily between Celsius and Kelvin. It's very, very easy. So I'll see you guys in class.